Okay, welcome to the afternoon sessions. And the first talk in this session will be by Zsuzsanna Baran, Intersections of Branching Random Walks in 8 dimensions.
Okay, thank you very much. And yeah, before I start, I would like to thank the organizers for the opportunity of attending this conference, but especially for speaking here. So I will be speaking about intersections of branching random walks in Z to the 8. This is based on a recently completed project, and it's also on archive with the same title, so you can search for it. I also wanted to say it might have some overlaps with the previous talk or like some clashing notation, but I just thought it's nice to keep it self-contained. So before I start talking about branching random walks, to give a bit of like context and motivation, I will talk a bit about simple random walks and in particular intersections of simple random walks. So let us just take consider two independent simple random walks on Z to the D. And let's take D greater than 2, so they are transient. And with one of them, let us consider the full range. And for the other, then let us just consider it up to some given time n. Are these colors visible? Yeah, okay. And we are interested in the intersections of these. So as a very first thing, let us just look at the expected number of intersections. So let us look at the expected number of intersections. So this is not that difficult to calculate because, the probability that one walk at time I, other walk at time j, coincide is just, the probability that a single walk at time I plus j is back at 0, and from the central limit theorem we have a very exact estimates for that. So with some calculations, you will end up getting that this is n to the 4 minus b over 2. Then the dimension is less than 4. It's of order log n when the dimension is equal to 4. And it's of order 1 when the dimension is greater than 4. And yeah, you see that like 4 is the critical dimension for this. And it's polynomial for for smaller dimensions, log n for 4 dimensions, order 1 for greater dimensions. So let us look at something more challenging. So let us look at what's the probability that there are no intersections. So these two ranges avoid each other. And for that, based on just this, you could conjecture, I think it was conjectured that it shows a similar behavior. So maybe it's decays polynomial in n for small dimensions. Maybe it's decays some power of log n for 4 dimensions, and it's of order 1 for bigger dimensions. And this sort of question was already studied, for example, by Erdős and Taylor in a 1960 article, and it's not that easy. So one thing that might be tempting to you might be tempted to do is the following. So might be tempted to try to estimate the probability of having an intersection by on that event that there is an intersection, looking at the first intersection and then doing some sort of Markov properties thing from that. But that's not really possible to do because you have 2 random walks. So there isn't really a way to define a first intersection point, so it's a stopping times for both of them. So these are one of the main difficulties. And I will be mainly interested in this critical dimension. So it was Loader who managed to sort of verify this, but in the 1990s. But the first thing he showed was not exactly about this probability. It was about a case when one of the walks is 2-sided. So he had one infinite walk like this, And the other walk was two-sided, so it's indexed by the integers, and the positive and negative sides are just independent random walks. And we look at it between times minus n and n. So he showed that the probability of this like two-sided and one-sided walk avoiding each other it decays like a constant over log n in 4 dimensions. And then later he also extended this result for a one-sided walk. So he showed basically what I wrote here. So he showed that this is basically the root of this probability. And I just want to emphasize that the amount of work required to go from the two-sided case to the one-sided was like at least as much like comparable to, to establishing this in the first place. Yeah, so maybe that's all I wanted to say about simple random walk, and I will start talking about branching random walks now. So I will start by defining what a branching random walk is. It will basically be a simple random walk indexed by some random tree, but in this case it will be a very specific random tree, the infinite invariant tree, which I will define. So I will start by defining what that tree is like. This will be associated to some distribution mu. So mu will be some distribution on non-negative integers, so it will basically be an offspring distribution. And let it have mean 1, so it's critical, and some finite non-zero variance, which we will call denote by sigma squared. And given this distribution, we define the infinite invariant tree as follows. And I will also say in a moment why it's called like that. So it has an infinite sequence of distinguished vertices, which are like joined up like this in a line, and this will be the spine of the tree. And then for the zero spine vertex, this will be the root, and we let it have some number of offsprings on the right-hand side. Let's say d plus 0, which is just distributed like mu. And then for a later spine vertex, for example, the ice one, we will let it have some number of offsprings on the right, this side, and some number on the other side. So the root didn't have anyone here, but here we allow offsprings on both sides. And I will write down how they are distributed. So this is basically just saying that if you look at this vertex, its overall number of offsprings on the two sides plus the one on the spine, it's just distributed like the size bias of mu. And once you know how many of them you have, you just like decide uniformly how many go on each side. So and these are all independent of each other. And then for vertices that are not on the spine, you just let them have like mu offsprings independently. So you're basically just putting independent Boltzmann-Watson trees here. And because mu is critical, almost surely all these trees will be finite. So it will be one-ended. This tree will be one-ended, so it has like only one way to go into infinity, and these like finite trees hanging off. And in particular, it's like possible to go around its boundary. So we will use that. So we will index the vertices of this tree by the integers just by going around this boundary and indexing vertices in the order we encounter them, so that the root gets shifted so that the root gets 0. So this is the tree, and then we just consider a simple random walk on Z, so the index by this tree. So another way of thinking about it is you take the tree, you put root to 0, and then everyone is a uniform neighbor of its parent. And then this will be a branching random walk. And so why do we have this object? So it is a very similar object was mentioned in the previous talk as well, and was considered like in a, for example, 1986 article by Kasten. Potentially it was also considered earlier. Like they considered like this object is like a similar object, but like instead of this tree, it's indexed by a Galton-Watson tree condition to survive, and that can be used as a sort of simplistic approximation of the infinite incipient cluster of a bond percolation. And so you might want to study to get some idea about what happens in an infinite incipient cluster of a percolation, which is really hard to study. And this particular tree.
Can I ask a question?
Yeah.
So just to make sure that I understand, so when you go on an edge of the spine,
yeah,
in one direction, and when you cross that edge, but in the other direction later, the two displacements of the walk, they're independent.
So this is one tree, which happens to have a distinguished set of vertices. But when you put a simple random walk on it, you just have each edge gets one displacement.
And the displacement will be the same when you go on the top and when you go later on the bottom of that edge.
No, so if you have a vertex here, so you assign IID displacement to each edge, and for example, on this vertex, its position will be just the sum of these 4.
Oh, okay.
But does it answer the question?
Yeah, okay, I think.
So you're not. Right. So this indexing did not appear yet.
Okay.
If there's a question.
Yes, please. Thanks.
Yeah. And yeah, so that's why it's considered. And this particular tree was, I think, introduced by and Shan, and then because it is have a very similar distribution. It's the only difference is the distribution of the number of offspring of the root. But it has a very big advantage, which is that it has a shift invariance distribution. So if you take the vertex that's index 1 according to this indexing, and that's why the indexing is important, and you reroute the tree and shift the walk on it so it becomes 0 there, then you just get an object with the same distribution. So, and I think in many works I already just studying this, branching on the walk with this tree and get a result for that, and do not necessarily, relate, try to transfer the result for that tree, which is a conditioned Galton-Watson tree condition to survive. So I will also be working with this tree. So what's the sort of question we are interested in? So again, we will want to look at intersections between two independent trees. So maybe I will start a new board. So, or intersections between two independent branching random walks. So I will just let T and T tilde be independent branching random walks on Z2D. And again, with one of them, we will consider the whole tree, or whole one side of the tree. So this will be say T. And with the other one, again, we only consider it up to some given index, according to this indexing. We will work with that. If you would consider it up to a given number of trees hanging off, it would get similar results. But maybe it's easier to work with just given number of vertices according to this indexing. So this is maybe T up to some n vertices, and we look at the intersections between these. So
what is n? N is on the spine? Or?
Yeah, no, so n is, according to these indices,
Okay.
you get...
From minus n to n.
For now, you just go from 0 to n. Sorry, a piece of notation I wanted to say. So I will write, maybe let's switch this word. So I will write T goes for the tree and the walk on it. And I will write things like tk to mean the vertex which has index k according to this indexing, and also the position of the walk at this vertex. And I also write things like tk, k plus I to mean the vertices with indices in this interval and the value of the walk on it. And you can also have open intervals and things like that. Yeah, so we want to look at intersections between one tree up to some given, like one walk up to a given time and the other walk, like the whole one side of it. And again, just to get an idea what to expect, let's just look at the expected number of intersections. So it's not that difficult to see what the Green's function of like a branching random walk is like. So by the Green's function, I just mean the number of times it's expected to hit a given vertex at a given point on, say, the positive side. But I mean, if you would define it on the negative side, you would get basically the same, and for both sides you just get a factor of 2, so it's not too important how it's defined. So it's not. So you can think over that this is basically like sigma square over 2 times the convolution of a Green's function of a simple random walk with itself. And the reason for that is that because you have a simple random walk along the spine, and then for each vertex except the root, like you have an expected sigma square over 2 vertices hanging off, and from there you just have critical Galton-Watson trees, so the Green's function is like a simple random walk. So that's where you get this from. And I mean, we know what the Green's function of a simple random walk is like, so you can like calculate that this is basically the case like x to the d minus 4 plus 1 for like the x to the d minus 4 for d greater than 4, and I will keep assuming d greater than 4. So okay, so we know how many times this walk, like this branching on the walk, will hit a vertex, but it's not really clear what happens if you consider it up to some given index n. So for that, I will just like give a heuristic argument to get an idea of what to expect, because this is like only for intuition, this calculation. So if you want to know what it means to consider the vertices up to some index n, we basically want to know how big these like trees hanging off the spine are. And well, I mean, like we have a pretty exact idea of how big a critical Galton-Watson tree typically is. So we know that the probability that it's greater than some size k is like constant over k. So if you take k of these trees, then you can think over that typically their overall size will be like of order k squared. So like going n indices typically means like going root n along the spine. And what does that mean in terms of the walk? So if you go some given number of vertices, so some given number of steps along the spine, and the simple random walk along the spine typically goes like root that many distance. So we can make so just for a heuristic argument, we could try to replace this tree up to like n indices with like the whole tree, but you only keep the vertices that fall in a ball of radius and to the quarter. And then if you plug that in, you would get that the expected number of intersections I mean, you would get that it's with some calculations, you would get that this is basically of order. This is of okay. So this is of order n to the 8 minus d over 4 for d less than 8, it's of order log n for d equal to 8, and it's of order 1 for d greater than 8. So, this looks very similar to, okay, this is also just an approximation so far, but like this looks very similar to what we have seen for simple random walks, right? And in particular, it like suggests that the critical dimension is 8. And based on this, we can also, like again conjecture like what we might expect for the probability that there's no intersections. So we can conjecture that it again like behaves like similarly to this. And again, like we'll be most interested in this critical dimension. And yeah, I think like I'm ready to state the first result, which is basically confirming this. But again, similarly to what we have seen for simple random walks, like Lawler's first result was about a one-sided and two-sided walk. And here as well, the results will be about a one-sided and two-sided tree. But yeah, so I will just write down the results. So we take two independent branching random walks on z to the 8, as it was mentioned, and then the probability that one of them, like in two, you go on both sides but only up to n steps, avoids the other one when you go on one side but like all the way, grows like a constant over log n, where this constant only depends on the variance of the offspring distribution, but not on the whole offspring distribution. Oh, sorry. So it's of order 1 over log n when this like this is up to constants, but those up to constants only depend on sigma squared. And actually, so if you also, Lawler had some exact asymptotics. It's not quite exact asymptotics, but if we also include some extra event, then we do get exact asymptotics actually. So this will be theorem 2. It's the same setup, same non-intersection probability, and you also insist that, we will see why it's important. So you also insist that this tree on the positive side, so on the positive side does not revisit 0. So then you get that then you get an exact asymptotic. And there is actually one more result. I will state that, and then I will state that as well. So there's one more result which is sort of a weak law of large numbers about the sort of the size of in some sense the size of a branching on the walk range. Like more precisely, it's about the branching capacity of a branching on the walk range. So again, I will just start by defining so I will start by defining the analog for simple random walk. We'll define it for branching random walk. I will state the result and I will talk about them.
So 0 is the position of the root?
Sorry?
0 is the position of the
yeah,
root?
sorry, I didn't say. They always start from 0 unless specified. Yeah.
So the same thing would not happen. So for instance, you don't know this result if I replace 0 by some vertex of z.
So if it's close, you would get, I think, basically the same result. If it's, I think the interesting thing is if it's a distance n to the 1/4 order, and this is, this is a more difficult to say. Like for for simple random walks as well, this was like a separate result that took extra effort, and it's also like in progress, but yeah. And like in that case, you would be interested in intersecting, I guess. So if it's closer than that, I think you would get basically the same. You would expect to intersect in general, and you would get a similar result for no intersection. If they are very far, they just won't intersect, and if they are here, then yeah, you can ask about the probability of not intersecting. Does that answer the question?
Yes.
Okay. So I will just recall what capacities. So, okay, so this is basically, I mean, I think most people might know this. So this is just, so for a set, a finite set in Z to the D, a capacity of A is just defined as a sum over the points of A. A probability that a simple random walk starting there would never return to A. And you can, so this is like a sort of notion of size in terms of the escape probabilities or like non-intersection probabilities with a simple random walk. And you can see that, like previously we talked about non-intersections between two simple random walks. So you see if you would put a simple random walk instead of A, you would again be talking about non-intersections between simple random walks. So let's see what we get if we would plug in a simple random walk instead of A, but it has to be finite. So just plug in a simple random walk range up to n steps. And it was, so you would expect that, you know, because you are summing over x vertices, so you are summing over n things here, and each of them has a probability of, and based on that about probability of log n-ish, not intersecting, you would get a, so you would get a, like an, and you would expect it to be like n over log n-ish. But anyway, so this in 4 dimensions. And this is something, like, this is not something Lawler looked at, I think, but this is something Asana, Shapira, and Susi looked at. So, I think in 2019, and they proved the strong law of large numbers. So they proved that this converges to some constant almost surely, and in L2. And our third, so the third result I will present is basically this, but for branching random walks. So for a branching random walk, you can define branching capacity in a similar way. So it is the sum over points of a set. Probably that the walk started from a branching random walk started from there, never returns to the set. But I mean, you look at the negative side of the branching random walk. I mean, this is just how it was defined originally. It doesn't make much difference. And this was introduced by, so this definition was introduced by True, I think. And so the third theorem basically says that if you have a branching random walk on Z to the 8, and you look at the branching capacity of it up to some given number of steps, and you scale it like that, then it goes to some constant, should have wrote more left, in probability and L2. So it's not quite an almost sure convergence, but it's like a weak law of large numbers. Okay, so these are the results. I will, yeah, I just want, okay, like I want to say a few, I will, for the rest of the talk, I would also like to talk about the sort of ideas of the proof, but there are just a few things I want to say about this first. So one thing is that I was mainly like talking about two branching random walks and contrasting that with two simple random walks. But it also sort of makes sense to look at intersections between a simple and a branching random walk, so that's something people did look at. In that case, the critical dimension would be 6. And then like, I think like Bai and Wan looked at the, where do I write? So Bai and Wan looked at the, I think they looked at the capacity of a branching random walk range, and they showed, this is all in 6 dimensions, so they showed a similar like weak law of large numbers. And then like Shapira looked at it the sort of other way around, and also showed a strong law of large numbers. And there has also been, and one of the difficulties in working with branching on a walk in general is that it doesn't have a strong Markov property the way a simple random walk does. So in all these previous works I mentioned, like at least one of the two objects was a simple random walk, and then they, like in the proof, the strong Markov property of that was like used, and we are basically not able to do that. So that's one of the main difficulties. And also I was like always talking about the critical dimension, like there has been also plenty of work on other dimensions, but that's just not what I want to focus on today. I just want to say that some of these articles I mentioned also like prove things for other dimensions, and there's also plenty of work on that. Yeah, so I think in the rest of the talk I will basically talk about the ideas of the proof, but maybe this is a good time to ask if anyone has questions. Yeah?
What happens if you don't have finite variance?
If you don't have finite variance, I think, so for example, just the expected, so for example, like one thing the variance immediately appeared is like just the expected number of vertices here, like sort of offsprings from the root, so that might already explode. So here, so okay, I guess my short answer is that I'm not sure. But I think what happens here just wouldn't work. Yeah. Yeah.
Yeah. So in your theorem 1, if you take 0n instead of minus nn, you expect to get also 1 over square root of log n?
Not. I think so. Yes.
But it's not known.
Yeah. No. It's
okay.
Also in progress. Yeah, but I would expect that, I think. Any other questions? Okay, maybe I will continue. I think I will erase this part. So the sort of like main ideas of the the main steps of the proof are actually so similar to what happens in the proof of these two results, but like how you can do each, like which both build on the work of Lawler but two simple random walks, but how you are able to do each step is quite different. So I will try to emphasize that. And the starting point for these previous results as well, and for us as well, will be something I will call a magic formula. So I will write that down and I will talk about it, where it comes from and why it's useful. So instead of considering the trees or the branching random walks up to exactly n steps, it will be more convenient to consider it a random number of steps with mean n. So I will consider it. So I will just define two geometric random variables with mean n. And I will write down the formula and then talk about it. So you consider one tree between these two geometrics, not intersecting the negative side of the other tree. You consider the positive side of this tree not containing 0. And you weight the whole thing with the number of intersections between this tree and the positive side of this tree. I will show in a moment why we are doing this. And the claim is that this expectation is equal to 1. so there is a very, if you would replace one of these trees with a, or like one or both of these, like branching random walks with a simple random walk, you would get the same formula with verbatim the same proof, because it only uses the shift invariance of the trees. And so basically, like, the proof is something like the following. Like, you start by, okay, like maybe I will say first like why we like this, so why we care about this formula. So the reason we care about this formula is because it features this event whose probability we want to compute. And also, if you look at, or like, which is basically the event whose probability we want to compute. And if you look at this, this is basically the event of theorem 1, and this is basically the event of theorem 2. And the way you prove it is, you start by writing down a probability that you know is equal to 1, and then you start like shifting the two trees. So you start by writing down that these two trees intersect, or like these two branching random walk intersect, which you know is 1 because like they just both contain 0. And then you start like shifting the trees around. So you look at the smallest index where t tilde intersects, and then you shift so that becomes the root. So that's why you know that at smaller indices you don't intersect. That's sort of where this term comes from. But in exchange, you have to wait with the number of intersections on the other side. And you also sort of shift this other tree so that the first intersection point becomes the root. So that's how it got shifted here. And this term comes from sort of, but because you want to consider each point of the range only once. So this is sort of saying that if you already saw this point of the range, you don't consider it again. I mean, you have to, like, I mean, this is a bit technical calculation, you have to write it down, but like this is basically just shifting the trees around. And as I said, the reason this formula is really nice because it features it's a simple formula, it features the probabilities we want. So this is what we want to pull out. This is like a number of intersections. So we could, I mean, like, it's so feasible that we could find the expectation of this. So if we could find the expectation of this and sort of like decorrelate these two terms, like we would be done. But I mean, obviously these two terms are like really not independent, because they both depend on the tree T, or like the branching random walk T. And okay, so one of them has the negative side of T tilde, and the other one has the positive one, but they are still dependent because the spine is common. So by the way, if T tilde was a simple random walk, then you wouldn't have this dependence because the positive and negative side of a simple random walk are independent. But we are not in that case. So I will talk about how we can try to decorrelate these terms. So first, you just try to show that this number of intersections is like very concentrated. So you will try to show that the expectation is like constant times log n, or I will write it like this because this will be the constant appearing in the theorem. And you want to bound its variance. And I mean, even just finding I said it sounds impossible, even just finding the expectation of this is like not really obvious to do like very precisely. Because as I said, it's not clear what it means to go up to given number of indices along the tree. So to do that, we do something like the following. So we consider the depth first few process, which is like a way of encoding a Galton-Watson tree in terms of a random walk. So it's a way of encoding a Galton-Watson tree with a random walk. And we will sort of try to find the number of vertices of T, like T as in the tree itself, that are at a given distance from the root. I think it's time to change this. That are at a given distance from the root. And so we want to find the number of vertices like that. We write down this, what this expectation is exactly. I mean, it will feature a lot of Gordon-Watson trees. We will sort of translate that to something about random walks with this depth first tree process, and then we manipulate that random walk, and then we reinterpret the result in terms of trees, and we'll get a very exact estimate of the number of these vertices. And then for the variance, you basically want to look at number of pairs of vertices of T as in the tree, which are like a given distance from the root and each other. And then, once you know these distances, you know how the simple random, like the random walk at these two walks relate to these 2 points that relate to each other. So you do some calculations like that, and you will end up proving this. Okay, so we have seen that this is very concentrated, so now we try to pull it out. Okay. So that will be we basically want to decorrelate these indicators from this counting thing. So again, we know that this thing is very concentrated. So we have good bounds on the probability it deviates from its mean. So we want to basically bound the probability that says that okay, this deviates a lot from its mean, and these non-intersections hold. And we try to split it into events, where these talk about different parts of the trees that are almost independent from each other. So what we do is the following: we consider a ball of some given radius around 0. I mean, this is set to D, so we consider a ball around 0 for given radius, and we consider we consider the first time that the spine of the tree T tilde hits the boundary of this ball, and it will have some trees hanging off like this. And we also consider the first time that the root of the other tree hits a given distance. The spine of the other tree hits some given distance from starting point. And first, let me just look at the intersections between these parts. We look at the intersections between these parts. We know we have a bound on we know it's unlikely that it deviates from its mean. And instead of requiring all these things not to intersect, we will just require some other parts of the trees not to intersect. So we will also consider a bigger ball of radius 4c, say. And we will just again look at when the spines of the trees hit that distance. And we will ask for these parts of the trees not to intersect. Not to intersect. So we see that these two parts of the tree are basically independent of each other. So we basically got some events that are independent of each other, and we also split similar. I mean, so we know. So this sort of thing when you have the number of intersections between these parts of the trees, and then you deal with the other cases similarly. So maybe you look at when one tree after it hit a given distance, other tree before it hits a given distance. Again, for this tree, the other side you will consider is, after it hits some bigger distance, and for the other tree, the other thing you consider is until it hits some smaller distance. So you have intersections between these, and there's sort of like no intersection even between these, and you do the other cases as well. So okay, so you will end up taking this term out, and you I will just like basically repeat what's written here. So you know that this event that was in the indicator, so this non-intersection event so you know that this is just a further constant over log n, or like asymptotically constant over log n, so you basically have theorem 2. I mean, it's theorem 2 has like n here, but like the geometrics are concentrated, so it's fine. And also, again, like this is just, you have to write down some calculations for the like definition of the branching capacity and like the shift invariance of the trees. But you basically get that this probability is also equal to, the expectation of a branching capacity of a tree at a time that at a time like that. So we basically so again, like the geometrics are concentrated, so like we can basically replace this by n. So you basically also get the expectation of the branching capacity you want, and then you bound the variance as well, so you get theorem 3, and there's like theorem 1 missing. So we want to for theorem 1 we just want to remove this extra element. So I will just very briefly talk about like what's the intuition for that. So if you had, okay, maybe I will just do it at the bottom of this board. So or like I will say n. So if you again, like let's think about it, what would happen if this was just a simple random walk. So if you have a simple random walk without like any two-sided simple random walk without any restrictions, and you have a simple random walk where you are insisting on the right-hand side not hitting 0, you can compare these as follows. So you could just consider the last time this walk hits 0, and so remove this bit in the middle. So you like stick these two things together. And you would get exactly a simple random walk with the positive side not having a 0. But we are working with trees, so if you have a branching random walk, so you have a branching random walk without any restriction, and you want to compare it to the branching random walk where you insist on the one side of it not hitting 0. So again, I will consider the last time this hit 0, but you can just remove the middle bit because that's not how branching random walks work. But instead, what you can do, you can also shift this to be the root. So this way, you will end up with, well, so this is the last 0. So this way, you will end up with a walk that, well, I mean 0 here, you have no zeros here because you shifted the last one, but you have to wait with the number of zeros on the other side. So you have to wait with the number of zeros here. So I will just write down one thing and then I will just write down here and then I think I will finish there. So you basically get that the event you want in theorem 1 so what you are sort of allowed to do is you insist that this tree doesn't hit 0 on the positive side, but in exchange you have to wait with the number of zeros on the other side. So yeah, you insist no zeros on one side, but you have to wait with the number of zeros on the other side. And when you shift this, like n changes a bit, but you can check that it doesn't make much difference, so you can still like write n's here. And okay, so this is what we want. This is what we want in theorem 1. This is what we have in theorem 2. This is something whose expectation we can like compute pretty exactly. So we just have to again decorrelate them. And I mean, it's again like not, I mean, it's surprisingly not easy, but I mean, again, you just like split this like number of zeros into like many smaller counters. Like you count how many of these descend from a given vertex, and you sort of group them based on the value of the walk at this spine vertex and how many time you visit that. And there are like different ways you can bound that, and like if you put all the bounds together, it ends up covering all the cases. So that's how we will end up with getting theorem 1, but in the process of doing so, we lose a constant factor. So that's why it's only up to a constant factor. Yeah, so that was the sort of idea of the proof. Yeah, I appreciate it was a bit technical, but yeah, so that's more or less what I wanted to say. And yeah, maybe I will thank you for your attention here. And
So if you are in a smaller dimension, less than 8, does your metric formula give you some bound, for instance?
so for bounds for
bound on for the probability of probability you are considering of non-intersection of the two branching random walks.
So I know that's not what you are asking. You probably know that. So the formula itself does hold. Yeah, I think it might give a similar bound, but like it didn't do that exactly. Yeah.
No, I think it's difficult to have the exact behavior, but maybe some bound.
Okay, I will think this over and like we'll try to get it.
Okay.
Do you have maybe an explicit expression for the limiting constant?
For the what?
For the constant C.
Oh, for the C. Yes, there is an explicit expression. I think I can't write it down right now, but like it is just, yeah, it is explicit because we do get an explicit expression on this number expectation, and then just that. So I think it's some like polynomial of sigma squared. Yeah.
So why is it so hard to get the one-sided estimate?
So I mean, like one of the things. So I mean, it was already okay. So if you, I guess it wasn't written down anywhere. So you would expect to be at sort of the root of the other one, but I mean obviously like even like one like the t tilde is the same in both cases. So like obviously it's not just the product, and like even for t the two sides are like heavily dependent on each other. So for simple random walks, what happened is that, I mean, you're probably familiar with that. You want to show that with a large probability. I think like one walk is such that the probability of another walk doing something to it is like something, and then so one walk. So the only common thing, the x tilde is removed this way, and for x the two sides are independent. But now even then the two sides of t would not be independent.
So maybe off-topic question, or you could relate to the previous question. Could you define a kind of random branching interlacement? Because there's this thing which is called random interlacement, which is like a simple random walk with two-ended, like goes to minus and positive. And for some reason, it sometimes is I think you do a lot of conditioning where you have a finite subset or finite box. You intersect it finitely many times with one of your trees, and you look at the first time or the last time that it happens. And this is also how you define like random interlacement, which is a random walk trajectory, and you have for every finite box, you look at the first time you're going to hit this box. And so forward, that's a simple random walk trajectory, and backward, it's a random walk condition to avoid that box. And then there is a kind of coherency from one box, from doing this from one box to taking a larger box, etc. So you can define some kind of double infinite random walks in that way. I was wondering if you could do this with branching random walk, with this branching random walks, like. This has been done already.
Yeah, it's already done already. Drew did it around the that would define the branching capacity, constructed this object in a series of papers.
Any other questions? Sorry? Well, 36 seconds of questions. Okay, now let's go to